All right, ladies and gentlemen, so today we're going to be moving on to a different type of factoring problem called, the difference of squares. And I'm going to show you something because we actually did these before, okay? So when I look at this, right, we had problems like letter A, and then I'll go back and do the definition. But we had problems like letter A where we only had two terms. And I told you that that really means that the middle term, the H term, would be a 0. Oh, look at me said, oh, sorry. Anyway, so that meant that I needed factors of 9 that subtracted to give you 0. So when you do your factor, when you do your factor and difference, because they were subtracting, our factors of 9 and 1 are 9, which gave me 8, 3 and 3, which gave me 0. So when we did our parentheses, and we ended up with a 3 and a 3, and in order for them to be 0, it was a plus and a minus. Well, this is called the difference of two perfect squares. So it's when we have the subtraction of two square roots. I'm going to actually add in perfect square roots. And a perfect square root just means that you can take the square root of it. So instead of having to go through and do this, it's done the same way all the time. You need the square root of both terms. Well, the square root of 9 is, well, what times itself gives me 9? 3. Square root of h, you're always, if it's for the exponent, you're always just taking it in half. So when I look over here at letter B, first of all, I'm looking to see, when I look at it, I'm like, okay, it's subtracting, there's two things. Maybe it's the difference of two perfect squares, which is sometimes abbreviated DOPS, DOPS. Anyway, and I could do that because the square root of 64 is 8, because 8 times 8 is 64. My exponents are both even, so I'm okay. So when I do this, I'm going to set up my parentheses. I'm going to take the square root of 64, which is 8, and it goes 1 in each parentheses. The square root of g squared, which is just half of that. So, sorry. So they each get a g. Then I have the second term, h squared, which the square root of that is h. One gets a plus, one gets a minus, and you're done. Now, I still have to, and we're going to actually get a little flow chart that kind of goes through and has you check different things. So when I look over here at C, I'm like, okay, these are not perfect squares. But the one thing I always have to check for is there a greatest common factor? And I can pull a 3g out of here, which means I'm left with 9g squared minus 1. This is now, inside this parentheses, is now the difference of two perfect squares. So I'm going to keep this extra 3g that I factored out. And now I'm going to do my difference of two perfect squares. Square root of 9 is 3, so I put 1 in each parentheses. Square root of g squared is g. Square root of 1 is 1. And then I get a plus, and I get a minus. All right, this is one of my favorite ones to do because it's kind of a no-brainer. Anyway, so when I look down here, I have two terms. There's no common factor that I can pull out, so I'm going to check, is it the difference of two perfect squares? My exponent is even, and 16 is a perfect square. So, the square root of b to the fourth, you're taking half of the exponent, so that's a b squared in each. And I can check that, because b squared times b squared is b to the fourth. You're adding your exponents. Okay. Square root of 16 is 4. One gets a plus, one gets a minus. Now, you also then need to check what's inside the parentheses to see, can that be factored again? It's called factoring completely. We talked about that. This one cannot, because it's a plus. Over here, I have two things being subtracted. This is an even, and so I have to say, well, can I take the square root of 4? Is there something times itself that gives me 4, which is 2. So this parenthesis stays, b squared plus 4. But now I'm going to take my b squared minus 4, and I'm going to factor that again. So they each get a b. Square root of 4 is 2, so they each get a 2. One's a plus, one's a minus. So this is now factored completely. All right, let's try letter E. So I have two things. They're being subtracted, and this is an even exponent. So I can take and factor these. So the square root of 625 is actually 25. Square root of x to the 4th, you divide that exponent in half, x squared. One's a plus, one's a minus. Now I'm going to double check. Can these be factored again? This one cannot because it's a plus. But over here, I have an even exponent and 25 is a perfect square. So I can factor that one. So this one stays 25x squared. And then I'm going to factor 25 minus x squared. Square root of 25 is 5. They each get an x. One's a plus, one's a minus. Okay, let's try another one. So when I look at this one, I think, oh, look at two things, difference of two perfect squares. The problem is that I have 5 is not a perfect square, neither is 45, and 5 is not an even exponent. So then I say, and I really should have done this first, is there a greatest common factor? So I'm actually going to kind of put this one down here so I have room. Well, I can pull a 5x out of here. So if I pull a 5x out, I'm left with x to the 4th minus 9. This is now the difference of two perfect squares. 9 is a perfect square, even exponent. So I can take and factor x to the 4th minus 9. So they each get an x squared. Square root of 9 is 3. One gets a plus, one gets a minus. And then I'm going to double check. Can I factor either of these again? Well, this is a plus, so that's not going to work. This is a minus, but 3 is not a perfect square. So that one is factored completely. Okay, let's try another one. So 6g to the 4th minus 96. Does 6 go into 96? I hope so, because otherwise I can't factor that because it's not a difference of two perfect squares. So 16. So I can pull a 6 out. I'm left with x to the 4th minus 16. Then I say, well, can I factor x to the 4th minus 16? Which I can. That's the difference of two perfect squares. So I have, they each get an x squared. They each get a 4, because that's the square root of 16. One's a plus, one's a minus. Now I double check. This one, x squared plus 4, can't be factored, but x squared minus 4 can. So I'm going to factor that. They each get an x. Square root of 4 is 2. One gets a plus, one gets a minus. Okay? All right. Letter H. So when I look at this one, I say, oh boy. So I can pull a 7 out. That much I notice right away. So I'm going to pull my 7 out. That leaves me with x to the 3rd. Actually, you know what? I'm not going to do that. I think I'm going to factor by grouping. So let me factor by grouping first and see what happens. So here I can pull a 7x squared out, which leaves me with x plus 3. And over here I can pull a negative 7, which leaves me with x plus 3. I guess I should have pulled out that factor. Sorry. Now I can put these together. 7x squared minus 7, x plus 3. Over here I can still pull a 7 out. So x squared minus 1, x plus 3. Now I can factor x squared minus 1 into the difference of two perfect squares. The x plus 3 stays. So x squared minus 1 becomes x, 1, 1, one's a plus, one's a minus. And then I just do a double check of all my pieces. 7, I can't factor anything. X plus 1 is factored. X minus 1 is factored. X plus 3 is factored. And again, originally I was going to pull a 7 out. I could have done that. I ended up just having to do it later. So probably should have stuck to that plan. Again, we're going to be saving the solving stuff for, we're going to go back and do all of those later as a separate little chapter. So Hopefully you found this one easy. This is one of my favorite ones. But any questions, as always, bring them to class. Have a good night.